Hi student, in this module we are going to learn how to generate random variates from different probability distributions. The probability distribution could be known or unknown. It could be sometimes simple or could be very complicated. So we'll start with different methods of random variate generations. First I'll start with the inverse transformation method, and we'll take few examples and illustrate in R, and then move to normal generator, and based on the normal generator we can also generate the multivariate normal distribution, multivariate normal variates from multivariate normal distributions. And then we'll move to another methods that is called the mixture structure, where any unknown probability distribution can be written as a product of two known probability distribution functions, and then where these two known probability distribution functions, easily the random variables can be generated from these two probability distribution functions. So based on that particular structure we can finally generate the original random variate from the original functions. So this method is called the mixture method. And then finally we'll end with the rejection sampling method, which is very important sampling methods and widely used in Markov chain Monte Carlo methods. That is our primary interest in these particular modules. And there we'll define how to choose the target density, how to choose the candidate density, and how it's need to be implemented in R. And then finally how to compare the original to the user defined codes in the rejection sampling, because a lot of R codes are available. Inbuilt R codes and R functions are available for different known probability distributions. So we'll use some examples with known probability distribution just to compare how good the sampling is. But in fact the rejection sampling can be used for all kind of probability distributions, whether it is known or unknown, it doesn't matter. So let's see how it's need to be done in the R module. We'll start with concept of generating random variates from standard and non-standard probability distributions, then general transformation methods, the simulation from a multivariate normal, and then finally we learn about the rejection sampling. The methods that are going to be discussed in this module are mainly in the light of Monte Carlo method, mostly rely on possibility of producing a supposedly endless flow of random variables from standard or non-standard probability distribution. Such a simulation is mainly depends on generating of uniform random variables on the interval 0, 1, because the uniform distribution provides the basic probabilistic representation of randomness on a computer, and the generator for all other distributions do require a sequence of uniform variables to be simulated. The basic uniform generator in R is the function RUnif, whose only required entry is the number of values to be generated. The other optional parameters are minimum and maximum, which characterize the bounds of the interval supporting the uniform. For example, you can write RUnif, then 200, say 200 samples you want to generate, then minimum 2 and maximum 6, that is for uniform AB, A is 2 and B is 6. But the one problem is that all the methods that we'll see are actually pseudo-random numbers. To overcome this problem, one can use R function, that is set.seed, which use its single integer argument to set as many seeds as required. For instance, one can just write set.seed 4, and you can generate 5 uniform random variate from 0, 1, and if you don't change the seed in the next run also, if you repeat the same, you will get the same random variate. And if you change the number integer within the seed, say I can change from 4 to 7, and the uniform random variate would be differently generated. So if somebody needs the same random variable to be generated, they can keep the seed unchanged. This shows that the seed determines all subsequent values produced by the random generator. In the overwhelming majority of cases, we do not set the seed which is then chosen according to the current time. But in settings where we need to reproduce the exact same sequence as I mentioned of a random simulation, for example, it compared two procedures of or two speeds, setting a fixed value of speed is reasonable. Next we'll move to the inverse transformation method. That is the first method that we are going to learn, how to generate the random variate from probability distributions, and widely used methods is the inverse transformation methods. Here probability integral transform allows us to transform any random variable into a uniform random variables, and more importantly vice versa. Suppose x has the density small f and CDF capital F, then we can write capital Fx equals to integration minus infinity to x small ft dt. And if u equals to capital Fx, then capital U is a random variable which uniform distribution 0 1. This is because, suppose if I write this expression, probability of capital U less than equal to small u, then you can write replace u by capital probability of capital Fx into capital F small x, and then you will take the inverse, then probability of F inverse F capital Fx into F inverse capital F small x, and that gives you probability of x less than equals to x, and provide F as an inverse. So we assume that there exists an inverse of F, so F inverse exists. Unless this assumption, we cannot write this. So we'll take one example here. Let x follows a logistic distribution with fx in this form, and CDF fx is 1 by 1 plus e to the power minus x minus mu by beta. Then generate 10,000 random variables using inverse transformation from the above probability distribution, and compare your program with the built-in R function R logis, that is small r logis, all are lowercase. So this function is inbuilt in R to generate a logistic random variate. Let's u equals to 1 by 1 plus e to the power minus x minus b mu by beta, that gives x equals to mu minus beta log 1 by u minus 1. Assume alpha equals to 1 and beta equals to 5, then the algorithm would be generate u from uniform 0 1 and derive x equals to mu minus beta log 1 by u minus 1, that will follow the logistic distribution with parameter alpha and beta. Alpha is the location and beta is the scale parameter. Let's see how it's need to be generated in R. Let first we set n equals to 10,000, u equals to R uniform n, that will generate a 10,000 random uniform variate, and x equals to, I'll use that same transformation formula that I have shown in the previous slide, 1 minus 5 into log 1 by u minus 1, and y equals to R logis n, location equals to 1 and scale equals to 5. This is the y is generated based on the inbuilt R function, and x is something that we generated based on the inverse transformation method. And here I am plotting two series by two histogram to compare whether they are same or not. Seeing the histogram, it seems they are almost same. A normal generator. So one way to achieve a normal random variable simulation using a transformation is with the Box-Muller algorithm, device for a generator of normal 0 1 variables. Say for if u1 and u2 are IID uniform 0 1, the variable x1 and x2 defined by x1 equals to square root of minus 2 log u1 cos 2 pi u2 and x2 equals to square root of minus 2 log u1 sin 2 pi u2 are then IID normal 0 1. Note that this is not the generator implemented in R, which uses by default the probability inverse transform method based on a very accurate representation of the normal CDF inverse by Q norm function up to 16 digits. It is advisable to use R inbuilt R norm function where the entries are in, the number of variables, number of variate need to be generated, and then mean and standard deviation to generate the random sample from univariate normal distribution. For example, if somebody wants to generate a random variable from normal mu equals to 25 and sigma equals to 5, then you can write R norm, n equals to 100. 100 is the number of variables that you are going to generate, number of samples that you are going to generate, and mean is 25, SD 5, and that will give you 100 random variate. Now we'll see another case study of multivariate normal simulation based on the univariate R norm function. First we'll see what is the basic concept on this. The simulation of multivariate normal distribution, say normal P mu sigma, where sigma is a P by P symmetric and positive definite matrix, can be derived from the generic R norm generator. For that you have to use the Cholesky decomposition of sigma as sigma equals to AA prime. Take the transform of A of an IID normal vector of dimension P leads to normal 0 sigma normal vector. That is, if we write capital X equals to A into capital Y plus mu, where capital Y is an IID normal vector of dimension P. There is, however, an R package that replicates those steps called RM norm. This is the function name, and that can be used from the library M norm T. That if you don't have the library already installed, you can download and install the library before you call RM norm function. Let's see how it can be done in R. So I set n equals to 5 and mu dimension I used the 3 dimension, mu equals to 3 by 1, C equals to 1, 12 and 2, and sigma would be 3 by 3 matrix. So there are 9 entries, and by matrix function I assign a 3 by 3 matrix to the sigma variable. And then the for Cholesky decomposition there is a function chol, CHOL, all lowercase. That function can be used to get the Cholesky decomposition. So A equals to, I write chol and sigma, then Y equals to matrix R norm 15, 3 and 5. So that 15 normal variates would be generated, and that would be converted into a matrix of order 3 by 5, and then finally X equals to Y plus mu, and then if you type X, then we will get the 5 multivariate normal variates generated. And then the same thing can be done without those codes by the M norm T library function, that is RM norm. So that can be done, just call the library first, and then you just call RM norm 5, then you have to specify the mu and the sigma. That will generate you another 5 multivariate normal variates. So anyway, you can, whatever you like you can do, but as the function already available, you better use the existing function instead of drawing from the basic concept. Now we will see how we can generate the random variates from discrete probability distributions. To generate discrete random variables, we also can use the inverse transformation principle, constructing a generic algorithm that will formally work for any discrete distribution. So to generate x from p theta is a probability mass function, where p theta is supported by integers. Let p naught is the p theta x less than equals to 0, small p1 equals to p theta x less than equals to 1, p2 equals to p theta x less than equals to 2, etc. And then generate a uniform random variable for uniform 0, 1, and take x equals to k if pk minus 1 less than u less than pk. So this is the algorithm that we are going to follow for all the discrete random variates generations. We'll start with a binomial distribution. Say generate x, follow binomial 15 0. P is 0.4. The probability values can be obtained by R function P binom 2. Then compare the same with R inbuilt function R binom in size and probe. These are the three entries of that particular function, that binomial variate generator inbuilt in R, that can be used and can compare with the user defined generator. If I see in R code, I'll define n equals to 15. Suppose n equals to n is the first parameter of the binomial distribution, and p is 0.4 as I mentioned, and number of simulation that I'm going to do is 10,000, and p is equals to replicate 0n because I'm going to assign the different probabilities. So t is 0 to n, and then probability equals to p binom, q equals to 1, size equals to n, and probability equals to 0.4. X is then replicate 0, and in simulation just assigning a new array of size 10,000, that is nsim. Now I'll use a for loop, that is I equals to 1 to nsim and u equals to uniform 1, where xi equals to t1 plus some probe less than u, and that if once we run this for loop, it will generate the random variates from binomial distribution with specified parameters. And this is uniform code that can be used for all discrete random variates. And to compare with the inbuilt R function, that R binom, I generate separately and plot both the series by bar plot. And if you see these two plots, there is no basic difference. They are completely same. So here is the list of all random variates generators in R. It is R beta, R binomial, R Cauchy, R chi-square distribution, exponential distribution, F distribution, gamma distribution, geometric distribution, hypergeometric distribution, log normal distribution, logistic distribution, multinomial distribution, negative binomial distribution, normal distribution, Poisson distribution, student T distribution, uniform distribution, Weibull distribution, even random wizard distributed matrix also can be generated. And these are the list of the random variate generators available that comes with the basic function. So other complicated variables and complicated distributions are available in different packages. So next we'll move to a mixture representation. As sometimes a complicated probability distribution can be written as some form of the product of two known probability distributions. For example, we can write fx equals to integration y gx given y into py dy for continuous y, or fx equals to sum over I pi gix for discrete y, where g and p are standard distributions that can be easily simulated. To generate a random variable x using such representation, we can first generate a variable y from the mixing distributions and then generate x from the selected conditional distributions. Marginal distribution and then selected conditional distribution. That is, if y follows py and x follows gx given y, then x automatically will follow fx. That is our intention for generating the random variate from. For instance, we can write student T density with v degrees of freedom tau v as a mixture like above, where x given y is normal 0 v by y and y follows chi-square v degrees of freedom. So generating from a TV distribution, the T distribution, then one could then amount to generating from a chi-square v degrees of freedom, and then from a corresponding normal distribution. If x is a, so for we can take another example. Suppose x is a negative binomial random variable, then x follows a negative np, then x has the mixture representation, and say x given y follows Poisson y, and y follows gamma distribution with n and p, where n and beta is equals to 1 by p by 1 minus p by p. In R we can set n sim equals to 10,000 simulation, and as I mentioned there that n of the negative binomial is 6 and probability is 0.3. So first we'll generate y from gamma with the specified beta, and so 10,000 gamma variate we can generate, and then finally x equals to r Poisson n sim y, and histogram is showing that the histogram is the random variables of random variables generated by the user function, defined function, and the line showing the actual fit of the negative binomial distribution. So its fitting is quite well, so it's almost same. But when you are going to use, you can use the dn binom function to generate the random variates from negative binomial distributions. This is in general, this knowledge would be useful to generate the random variates from new distributions through this particular method. And finally we'll move to rejection sampling. So this is very, very important sampling technique, and very, very important in the context of Markov chain Monte Carlo methods. There are many distributions for which the inverse transformation method and even general transformation will fail to be able to generate the required random variable. For these cases, we must turn to indirect methods, that is, the methods in which we generate a candidate random variable and only accept is subject to posing a test or some criteria. These so-called accept rejection methods or rejection sampling requires us to know the functional form of the density f of interest, called the target density, up to multiplicative constant. We use a simpler density g called the instrumental or candidate density to generate the random variables for which the simulation is actually done. The only constraints we impose on this candidate density g are that f and g have compatible supports, that is gx greater than 0 when fx greater than 0. There is a constant m with fx by gx less than equals to m for all x. So these are the two constants that we need to impose, and the algorithm would be like generate y from g and u from uniform 0 1, then accept y if u less than equals to fy equals to m gy, return to 1 otherwise. So this is the algorithm, and now we are going to implement this algorithm in R with some suitable examples. Suppose for example 1, I'm going to use a beta distribution with parameters 6 and 3 from a scale uniform distribution by rejection sampling method. Let's see how it's need to be implemented in R. So here is the R code to implement rejection sampling of 1 lakh observations in this example. Suppose first we generate xx as a uniform 1 lakh uniform variates from 0 and 1, and define accept equals to c empty column, and then we use a for loop I equals to 1 to the length of xx, that is 1 lakh, and then within the for loop the algorithm will implement here u equals to uniform 101, that is one uniform random variate would be generated first, and then if the d unif xi01 into 3 into u less than equals to d beta xx1 6 3, then accept I equals to yes. Else if d unif xxi01 into 3 into u greater than d beta xxi 6 3, accept I equals to no, and then finally y equals to data dot frame xx, then accept equals to factor, accept, label, see, yes and no. So this YY will provide you that data frame where XX would be the generated random variates and accept will give you whether accepted or rejected. And now we can now plot the simulated data with true distribution as follows. Suppose X equals to, I am taking a sequence from 0 to 1 with 10,000, length is 10,000. So sequence from 0 to 1, there is a 10,000 real number would be generated sequentially, that is in increasing order. And then SQ another sequence I took from 0 to 1 by increment of 0.01. Then I draw the histogram as YY, then Y dollar accept equals to yes, comma 1, and then break is SQ, then frequency false, main is a histogram of XX and XLab is XX. That will give the histogram. And then finally I draw overlap a line, that is superimposed a line of beta distribution, the actual beta fit of the same parameter 6 and 3 that was mentioned over the histogram and showing with perfect fit over it. So density of the accepted and rejection values can be seen. So that to display this, I'll take the help of the library ggplot2, and in the library ggplot2 I'll use the function called qplot. So qplot print qplot xx data equals to yy and geom equals to the density and color is accept, that the variable that I assign in the data frame. And that will give you the density of accepted and rejected values. And next we can do a stack histogram, that is print qplot xx data equals to y, geom equals to histogram, fill equals to accept, and bandwidth equals to the bin width equals to 0.01. Then we'll get a stack histogram over this, and the rate of the acceptance can be improved choosing appropriate scale value here. Then we'll move to the another example, that example 2, as another simple example to illustrate the rejection sampling method. We'll sample from Pareto distribution fx beta to the power alpha, alpha beta plus x to the power minus alpha plus 1, where x greater than equals to 0, with the parameter alpha equals to 19.5, beta equals to 15.7. Then select gx from exponential lambda equals to 1. So gx is assumed to be exponential distribution with lambda 1. Then fx less than 10 by 7 gx we assume. To implement this, first we assign alpha equals to 19.5, beta equals to 15.7. Then target Pareto, we have to define the target function. So the target density, the target Pareto equals to function x, and then I'll write that expression beta to the power alpha, alpha beta plus x minus alpha plus 1 in R format, and then m is assumed to be 10 by 7, that is already specified, and the Pareto kernel times m can be covered by exponential lambda 1, so x equals to sequence 1 to 600 divided by 100. Then we can plot the x with density of exponential distribution, that will give, this plot will give the density of exponential distributions, and then the one line, the dotted line is indicating the actually the target Pareto distribution, and so the one is gx and another is m fx. The dotted line indicates the m fx. So now we can assign temp equals to REXP 10,001 and temp equals to temp less than 6. We'll take the all the temp value, I mean the exponential variate from 0 to 6. So we are restricting up to 6. Then U equals to uniform, that length of temp 0, and DEXP temp is the 0 to that up to 6 or whatever it is. So y equals to 10, u less than equals to 0.7 into target Pareto 10, and then that y will give the random variate. The histogram, we can draw the histogram again. Y probability equals to true. In class we can assign as 20 x lab values, and mean we can write rejection sampling method, and we'll again superimpose the line by the target Pareto x in the blue color, and then legend the top right we can write the Pareto kernel indicates. So that's how you can assign the legend over there. So it's saying that there is a nice fit over there. And few notes for rejection sampling. There are an infinite number of candidate density gx and constant m we can use. The only difference between them is computation time. If gx is significantly different in shape than fx, and if mgx is significantly greater than fx, then more of our candidate draws will be rejected. The algorithm become very slow. So if fx equals to mgx, then all our drawn will be accepted. So we have to find a m that is very closer to this equality. It may not be equal, but it would be quite closer to this equality to get a better acceptance in this acceptance sampling. So in this module, we actually saw three different methods that are, one is the inverse transformation methods, then the normal generator, that is the normal generator. Of course, normal generator was something that we defined is actually the waste of time, because there are two random variates were generated at a time. So that's why I recommended that always use the inbuilt R function for random variate generator. And then we learn about the mixture methods, and then finally we end with the rejection sampling methods. So rejection sampling, that is very important one. I guess whatever the examples that I have illustrated here might help you to apply wide variety of probability distributions using random sampling. But random sampling is not the end here. There are a lot of modifications of random samplings will come in future. So my guess is whatever I illustrated here might give you a basic concepts of generating a random variates from of course both from known and unknown probability distribution. Sometimes the probability distribution could be very complicated. So a lot of other methods are there. We'll learn in a sequence.